I'm going to be talking today about monorepos and reproducible builds, and the journey that the team that I'm on kind of went throughout our kind of DevOps journey and where we got to where we came from, in the hopes that some of the lessons we've learned along the way would be applicable to other teams. So I'm Austin Burdine. I'm a senior engineer here at Red Ventures, AC Burdine pretty much anywhere on the internet. So a bit of backstory before I get into kind of the monorepo, reproducible builds, all of that. A bit of backstory on how we got there, or how we came to that point. Prior to 2018, we were, for the most part, an on-prem PHP, lots of spaghetti code, PHP kind of development environment. And we were one of the first teams at Red Ventures to start really thinking about moving a lot of our stuff to the cloud. To give a very high-level overview of some of the stuff that our team does, we operate, we process orders, and we do that through both a sales center and through a web cart application. And so we kind of have two sides of our business that do similar order processing, but through different means. And we were, from some external factors, we were working on redoing a lot of our sales center flow from this on-prem legacy PHP environment that had all these problems to kind of a cloud-native, AWS-driven workflow. And so that takes us to 2018, and we spent probably the better half of 2018 actually implementing this. So we did Docker, we did a combination of a few different languages, we did deployments, CI/CD, that kind of a thing. And we kind of ended up with this flow a little bit where we had Terraform to do all of the infrastructure provisioning, so we adopted infrastructure as code. We had GitHub for code hosting. Yeoman is that there for generating new services, so engineers could spin up a new service in a matter of minutes. We had Jenkins to actually do the deployments. It's on fire because it's Jenkins, and that's what happened a lot of the time, but I'm sure most people here probably have some familiarity with that. And then all of the containers themselves were run on ECS in Amazon. And that actually led to a very quick and reproducible infrastructure spin-up process. So you could get essentially from nothing to a service deployed in production in probably half an hour, depending on how complicated the service was and all that. And so it led us to building out this kind of stuff very quickly. Unfortunately, because we had ended up with so many services, that money with wings ended up flying to Amazon for a lot of these services because they're expensive to run after you get a bunch of them. And also the problem is we made it to production, and then we kind of realized, okay, we've got all these services. What do we do now? And we kind of got stuck in this. We built out all these services and never thought or did not necessarily plan ahead to the actual maintenance lifecycle. And I say all this to kind of say, we had self-service. We had a good infrastructure deploy and provisioning workflow, but without kind of taking a look at our coding practices, that didn't really help us much and actually caused us more pain in the long run. So kind of where we ended in maybe 2/3, 3/4 of the way through 2018, we had 20 different microservices, and I put that in quotes because we did not do microservices as they were intended to be built. So in practice, these microservices were really a distributed monolith, a lot of shared code, incredibly tight coupling, which meant that deploying one service meant you had to deploy multiple at the same time, or otherwise things would break and nobody had fun. And also dependency updates for 20 microservices, especially with security vulnerabilities, it's lots of fun. And probably between 40 and 50 different repositories with the code for those microservices, any shared dependencies, any CLI tools, all of our deployment workflows, spread across 40 to 50 different repositories. So trying to tell somebody where code was a bit of a, well, it might be here, or it might be there, who knows? Lots of languages. So this list has shortened some since, but we had a combination of PHP, C#, Java, Node.js, and some Python, which if you're trying to introduce a new engineer to the team, it's really hard to have them learn all these. to maintain different parts of our stack. Deployments, despite having a very quick flow to get to nothing to production, over time became slower because of how we did our Git branching. So in order to get code to production, you would have to create a PR to our development branch, which would then get it into our development environment. And then once you were good with that, you would have to get it to master, make another PR, that would go to staging, and then to production, which worked, but say you had to get a quick fix out, and yes, you can do hot fixes to master, but then it essentially, if you wanted to get a code out the right way to production, it took maybe half an hour or longer sometimes from a developer's laptop to production. And so that was not as fun. And like I mentioned before, cross-service deployment organization was tricky because all of this tight coupling led to services that depended on each other breaking if they weren't deployed in the right order. And there was also very little consistency across these service APIs. So they were all JSON, but the actual structure of those API requests and responses was all over the place. Some used some methodologies, some used others. Very little consistency. And as we got past and launched this new phone sales center flow, and we started to add more stuff, looking to the future to redo our web enrollment flow, we started looking at stuff we would have to build out for that. And it became a question of, where do we put some of this new code? Does it belong in this service or that service? Do we create a new service? Because we didn't want to do that. And it was all really confusing. So new infrastructure for team members, explaining stuff to them felt somewhat like this sometimes. Just trying to say, it's here, it's there, this connects to that, this database has all this stuff, this database has all this stuff. Ultimately, it was confusing. Also, there was very little documentation. It was not a fun time. So as we kind of looked through building out this new flow, we decided to look into serverless a little bit, and mainly because a lot of our microservices were very simple. There was a couple of them that were one HTTP endpoint that made one database request and returned data from that database. And that was it. That was all the service did. And yet it cost $5-10 a month to run 24/7 for very few number of requests. And to add some more context to that, our business is not one that does Google-level traffic. We do significantly less than that, and so we did not have the need for some of the scalability that microservices gave us. That's not to say that microservices are the wrong choice for other teams, but for our team specifically, we found that microservices did not really address the problems that we had. It actually compounded them because we did not rethink our coding methodology to use microservices in the most effective way. So that leads us to when we started to consider serverless. We decided to build out this one process that was a really good fit for Lambda functions. And as I mentioned before, the microservices stuff that we were working on, some of those were really mapping well to Lambda functions because they were a simple HTTP request that made one database call. And so looking into serverless, we thought, okay, we've got this deployment process that works. How are we going to deploy serverless? So we looked into the couple of options that were around at the time. So you had Apex, which has since gone into an archival state, and then you have serverless, which has become a really popular method of deploying serverless infrastructures. And the common thing that we found for both of those deployment things is that they used monorepos to organize the code. Having a code, the Lambda is intended to be split up into lots of small parts, and so putting one Lambda per repo means that we already had 40, 50 repos, try 100, and that's not something we wanted to do. And also another thing that we wanted to try and solve for was our merge to development, merge to master, the fact that that took time, getting PRs approved. We wanted to kind of try out a trunk-based development approach, which means that every commit to master goes out to production. Now, there may be an approval step beforehand, but it means that you can basically just merge code in and it all works. And those were kind of the three things that we wanted to address. We wanted to do serverless, we wanted to do a monorepo, and we wanted to do trunk-based development. So one place for, and the other thing is we wanted to do one place for all code, not just our Lambda functions on the back end, but also our front end code. Because we thought, let's take a page out of Google's book and just throw everything in there. Like, why have multiple repositories if you can have one? And so that was the idea we had, the trunk-based development. So instead of 5 different languages, let's go to 2. Let's do Golang on the back end and JavaScript on the front end. And the nice thing about the monorepo is that any sort of cross-functional deployments can be achieved with one commit, instead of having to go update a shared dependency and then go update the version of that shared dependency in 5 different services. You can deploy all of them at once with one commit. And yeah, like updating shared dependencies is easy because they're all referenced in the same repo. The tricky bit that we ran into was, okay, how do you deploy this monorepo? Especially when you're considering that there's Lambda functions in there, but there's also front-end code. There were Lambda edge functions, which are deployed using a different mechanism than Lambda functions. And so because Apex and serverless kind of pointed us at a monorepo approach, we decided to look into both of those kind of to start off to see, okay, what do these have? Would these be a good fit for our deployment process? And we did run into a couple of problems with Apex and serverless. And these are problems that we had, not necessarily problems with the tools themselves. The problem we had was that it owns creation of resources as well as updating code. So serverless under the hood runs on CloudFormation, or at least it did at the time. And so when you would deploy your monorepo, it would create any Lambdas that did not yet exist, as well as deploy the code for those. And we had already had a really successful Terraform workflow for creating our infrastructure. And so it didn't really play nicely with each other, because if you have your Terraform and that's responsible for creating your infrastructure, serverless and Apex want to also own that. And so you get this weird mix of, okay, this does infrastructure, this does infrastructure. Where do we actually need to do things? And so, like I said, not super compatible with the Terraform. And the other big thing is that Apex and serverless are also, they have a model of all or one deployments. And you can kind of customize that a little bit, but by default, they will either deploy one or a specific set of Lambda functions, or they will deploy your entire repo. And the problem that we had with that is, if you're deploying your entire repo every time, you lose track of what actually changed. And so you deploy all your Lambdas, stuff starts to fail. Okay, what broke? Was it because we redeployed it? Or was it because this changed? And not knowing what changed leads to a lot of trouble with debugging. And also, at the time, Apex and serverless were scoped primarily to Lambda functions. Serverless has since released some stuff called like serverless components, which supports multiple things other than just Lambda functions. But at the time, serverless was pretty much Lambda functions, and that's what it was used for. So given that we had all these problems with Apex and serverless, we decided, okay, let's build our own, because we have these problems, we need something to solve them, and so build something that we want. And we had 3 kind of requirements that we wanted to set out for it. We wanted to say, only update code, don't create the resources, leave the resource creation up to Terraform, because that's what it's good at. Support multiple deployment types. Like I said, we had front-end code, back-end code, Lambda edge functions, all in the same repo. We wanted it to be able to deploy all those, and deploy all those in a relatively similar manner. And also, the biggest requirement was that we wanted it to only deploy changes. If a commit only changes one front-end site, doesn't touch any back-end code, we don't want to deploy all the back-end, because it doesn't need to be. The trickiest question we had to answer was, how do you determine change? Obviously, Git is how the repo is managed, and Git is used to determine changes to source code. So our first approach was actually using Git diff, which actually works to some extent to track source code changes. That's what it's really good at. But the problem that we ran into is that code can go through a number of steps from your source code to your final built deployment artifact, such as compilation or combining files or replacing environment variables for like front-end JavaScript. And also, Git diff, if you're using that to generate, to determine what to actually build, such as like, oh, this file has only changed, only compile this file, then you run into cases where, okay, if we're comparing these two commits, these things have changed. But if you're comparing these two commits, these other things have changed, and actually we might need to build other things. And so it becomes really tricky if you have multiple commits merged at the same time to figure out what's actually built, and determining the diff before compilation, you might not build everything that you need. And also, dependency graphs are a pain. Anyone that's worked with node modules is familiar with the pain. But shared dependencies, third-party dependencies, all of those factor into your changes. And building dependency graphs gets really tricky. Go has the ability to do it. Node, you can kind of figure out how to do it, but it would be very manual. And also, or it'd be a lot of manual coding to figure out a process to actually make it work. And it would also be very language-specific. Different languages import things differently, and so you'd be writing a lot of language-specific diff tools to do the dependency graph changes. And so at the time, when we were thinking about this get diff approach, I remembered a talk I went to at an All Things Open conference in 2017, and it was actually, I believe, one of the Fedora project maintainers who was talking about something that he'd been working on called reproducible builds. And the concept behind that is your build process becomes deterministic enough that you know, given the same set of source code and all of the external environment variables, build environment, all of that, if you can control all of those, then somebody else should be able to take that source code and get to the same build artifact with verifiable, like via cryptographic hash. So like if you take your built zip file, hash that, compare that to the zip file built using the same process by somebody completely different, you can verify that it's exactly the same. And this kind of goes above and beyond just normal checksums. Like checksums will let you know that this file, when it was built, had this sum, and you can kind of compare them to make sure it's the same. But reproducible builds, you can actually say, this source code specifically, we know, generated this hash. And so a build is reproducible. This is the definition from that project's website. A build is reproducible if given the same source code, build environment, and build instructions. Any party can recreate bit-by-bit identical copies of all specified artifacts. And the reasoning that the Fedora and I think the Debian project did these things was for security. Because if you're installing these compiled binary dependencies, you don't necessarily know if there's been extra code that's injected into them. Like if somebody has the ability to upload the checksum and a file, then it doesn't matter if the file matches that checksum because you don't know that that source code necessarily made it into that binary artifact. And so that was kind of the reasoning why they did it, but we're not as much concerned about the security because our stuff's not open source. But the reason that it made it really nice is that we know that if the same code equals the same artifact, then we know what changed, including our build environment, including our environment variables. We know after they've all been built what actually changed. Very easy to determine. You just compare the two hashes of two different files. If they're different, something changed, and you need to redeploy. If not, nothing changed, you're good. So what we kind of ended up with, and this is just a screenshot of kind of what shows up in one of our Slack channels, is when you commit, it builds everything in the repo, and then kind of compares hashes of things, and then it'll send a message to our Slack channel that says, this commit had these changes, and that button will take you to where you can deploy those changes out. So kind of a summary of it, all code in the entire repo is built on every commit. It's uploaded to S3, which is prefixed via the commit hash, and then S3 actually gives you an etag field, which is used for caching in the browser and used to invalidate that, but it's actually a really convenient MD5 hash, which isn't cryptographically secure, but that's not what we're worried about. It's really easy, and you can get it on a list bucket call, so it's computationally cheap as well to compare across commits. And then deployment changes, we kind of took a note out of how Terraform's set up, where they have a plan and an apply. The plan will list out all of your deployment changes, and then you take that plan and you can apply it, and all those changes are then updated to the various sources. So this kind of addressed those three problems that we set out to solve in the beginning. The deployment tooling uses native APIs to update code artifacts. It doesn't do any sort of creation of functions that don't exist. In fact, our deployment process right now will error if a resource does not exist in your infrastructure, because if you haven't created your actual Lambda function that you're updating, and then you make another change, if we ignored that missing resource, if you tried to deploy it later, it wouldn't know that something had not been deployed, and you'd actually have to change that artifacts to get it to pick up that deploy change. And so what we did to accomplish kind of the mapping of metadata, because you've got multiple environments, and you want to be able to map, okay, my function production is, you don't want to name that folder my function production in your repo, you just want to call it my function. And so the mapping of metadata, we built a custom Terraform provider that provides a very minimal metadata map of, here's the Lambda function, here's where it is in code. For the static sites, it's like, here's the S3 bucket, here's where it is in the repo. And so that deploy tool can kind of figure out where to send things. It supports multiple deployment types. So everything is an archive file. So either zip, tar, targz, including Docker. I'll get more into that in a minute. Each deployment type knows how to check for changes and how to deploy itself. So our Lambda deployer knows how to check for changes to Lambda functions and how to deploy changes to it. Lambda Edge, same thing. Static sites, same thing. Docker, all of it is kind of contained within its own deployment type, and it all knows how to do what it needs. And also, deployment types have a specific order. So what we figured out is that if you deploy multiple different types of things in a single commit, you might need to know in what order to actually deploy them. Like you'd want to deploy your backend before you deploy your front end changes, because then you could run into kind of a weird case where your front end's updated, your backend's not, API requests might fail. Generally, if you run into a kind of case where that would happen, you'd want to split them out into separate commits, and most of the time we do. But in the case where you end up with multiple changes going out at once, we had to specify the order so that you don't run into weird incompatibilities. And then only deploy changes. So artifact hashes are used to check for changes. If that hash is the same, we don't need to deploy it. And so that solves all of our kind of problems that we set out to solve. Okay, so the big question is, how do you actually make your builds reproducible? The Reproducible Builds project publishes a lot of tips to how to do this, but a lot of those that I found were a lot more scoped to like package distributions for binary things that you would put on like an operating system. And there weren't as many guidelines for how to do it with like a web service or a Lambda function or a static site. And so we kind of had to figure out some of this on our own. But ultimately, the core idea of making a build reproducible is removing any sort of randomness in your build process. And so there are a few sources of randomness that we found and had to remove. The first one is dependencies. So either, excuse me, any sort of shared code or any third-party dependencies, that can be a source of randomness. The build environment can be a source of randomness. And zip and tar can be a source of randomness because there's some weirdness with those that I'll get into in a minute. So the first one, dependencies. A lot of, at least the dependency management tools that we've used actually provide ways of reducing dependency management, and this, or dependency randomness. And this isn't so much from a reproducible builds aspect as it is from a security aspect. So Go, its dependency management tool, will provide a sum of the files that you've loaded so that it can compare and make sure that somebody's not trying to introduce a vulnerable dependency or a dependency with changes into your build process. Same with Node. The Yarn package manager includes checksums in a lock file so that you know that dependencies aren't changing underneath you. And these are, I mean, it's for security and it's for making sure that a dependency doesn't get updated without you knowing and then suddenly your stuff breaks. And so surprisingly, that was actually really easy because a lot of the dependency management tools provide those tools. So in order to kind of take advantage of that, you have to make sure that any of those lock files are included in your repo, which is generally standard practice, but that's something that I've seen some people ignore and something that you have to include in order to take advantage of those. And also vendor if possible. So we vendor our Go dependencies, which means including them in the repo. We don't do node modules because of the gravity well that is and the fun that it is not. But if it is possible, vendor the dependencies. That way you know that it's faster from a build perspective because you don't have to refetch all of them, but it's more secure that you know that stuff isn't being changed during a download. So build environment's the second one. To do that, you kind of want to use as specific of a version as possible for compilers. So for example, the Go language, you would need to specify a specific patch release of Go to use instead of just the minor version, because even patch versions can change how things are compiled internally. And what we found is that if you bump a patch version, generally a lot of things will change because something's changed in the compiler. Not necessarily anything that's broken, it ends up with a different hash. And the nice thing about this is build environment changes are treated as code changes. So you have a commit that says bump Go version to whatever the latest Go version is, and it's treated as a code change. And if stuff breaks, you know that it was the code change or the version change that actually broke it. And the last one is zip and tar, and this probably was the trickiest one. So tar is actually somewhat straightforward if you pass it 8 different flags or 7 different flags. A lot of it is alphabetization of files inside the archive, as well as extra attributes that files have, as well as modified timestamps. It actually only works with the GNU version of tar. macOS has the BSD distribution of tar, so you have to have the GNU version of tar to actually get it to work, which was fun to find out why it didn't work on my computer. Zip is a bit more complicated. Unfortunately, Lambda functions will only let you use zip. And for most of the Lambda functions, actually, for a while, it was fine because the zip files themselves were like just single files. You had a single binary that Go gave you. And with single files, zip is actually pretty easy. But with multiple files, it gets a lot more complicated. And what we had to do was basically incrementally add files in alphabetical order to the zip to actually get it to be the same every time. There was a lot of fun bash scripts that we wrote. Ultimately, it's a pretty straightforward process once you write it, but until you get there, it is a little confusing. And also, last modified time will mess you up. That's probably one of the biggest sources, because every time you're compiling a file, so that last modified time is going to be different every single time. You kind of have to set that to a static time in order to kind of remove that source of randomness. And then I'll kind of end on this. A note about Docker. We had to build support for Docker into our monorepo. Unfortunately, we had some longer running ETL processes that took longer than 15 minutes, which is the default Lambda timeout. And so they were kind of scheduled tasks. And so we had to build that out, build Docker support out. And it does support archive. So you can like save a Docker image to a tar file and then reload it and then deploy it. But those tar files are not reproducible in any sense of the word. Our resulting Docker images are essentially the same as a Lambda function, but like it's a Docker scratch image, so 0 dependencies with a binary inside of it, and yet it is not reproducible because, and I actually dug into this for a while, it's because of the modified timestamps, again, because they're not stripping those, because it wasn't a factor in that considering. What we ended up doing to kind of somewhat alleviate this process is enabling layer caching on our builds, and that got us most of the way there. So we'll still see some times when the Docker images just change for whatever reason, but that's kind of how we got there. So a quick note on how we build everything. Parallelization is your friend. Use the language tooling features that support parallelization. Go does this. Node has some things that you can use to parallelize compiling, building, all of that. When that fails, use GNU Parallel. It was a lifesaver. It halved our build times or more because you can parallelize things, use all available CPUs. Also build multiple types in parallel. So if your deployment system lets you run multiple containers at once, just build each type on its own in parallel, and then you're all done at the same time or roughly the same time. So drawbacks to this system, configuration change versus code change. So if our Terraform configuration for a Lambda function changes, that's not tracked the same as a code change, and so it can get weird sometimes with that, and that's something we haven't quite yet figured out how to address. Docker, as I mentioned before, has some problems with reproducibility. Maintenance of deployment code, so instead of it being a separate system that you just configure, the maintenance or the deployment code lives in our repo as well, and so if something breaks in that, you kind of have to go in and fix it. Lots of merges at once can get weird because you're comparing changes between one commit and the next, and so if you have multiple commits get merged in at once, you kind of have to cancel builds until, and this is kind of specific to how our commit comparison stuff works, but it's one of the limitations of our thing at once. Database connections are also a limitation, and this is mainly of serverless itself and less our deployment process, but it's one of the reasons why we wanted to reduce the number of changes that we deployed, because every time you deploy a Lambda, if it has a database connection, it's going to create a new one, and that old one may not be cleaned up. And what we found when we started deploying Lambdas is that we very quickly ran into connection limits, and that was a fun error to debug when stuff started to just randomly fail because it couldn't connect to the database. Yeah, and that's it.